thank you so much for your invitation. So it's my great pleasure to present my several years work on the blood clotting. So there will be 3 parts in the talk. So first, I will give you some brief introduction about the biology background of blood clotting, and then some challenges associated with mathematical modeling for the blood clotting. And then different type of model for studying different aspects of the blood clotting will be present in the second part. And then I will give the conclusion and talk about the future work. Okay, so in order to give you a quick brief review about blood clotting, so just to show you a YouTube movie. I hope you can hear the voice.
Even under physiological conditions, a small tear can appear in the wall of a blood vessel in order to prevent blood loss. Platelets and coagulation factors, such as the pivotal factor 10, acting in a coordinated manner, close this wound. The platelets are responsible for a first sealing of the tear. Then, a number of coagulation factors are activated, leading to the formation of fibrin strands which stabilize the growing clot.
Okay, so from this very short review, you can see that the blood clotting is actually very normal. So when you cut, so the blood clotting will simultaneously activate to stop bleeding. So it's very, very efficient. So at the same time, the blood clotting normally it will be automatically resolved after the wound is cured. It will be automatically resolved. However, the blood clotting can also be triggered by some pathological reasons, such as inflammation. Okay, so in this case, the blood clotting is called thrombosis. So actually, it's quite important, especially when you read the review article about the coronavirus 19. So this paper I shown here, so it gives you some pathological and some other explanation for the coronavirus. So it mentioned that actually during the coronavirus, it will induce some inflammation of the alveoli in our lung. And then this inflammation will induce some agonist called cytokine and IL. So this agonist will trigger the formation of the blood clotting, or it's called, in this case, it's called thrombosis in the alveolar capillary. So in this part, it will block the blood flow in this small capillary. Then it will induce a big problem such that the oxygen cannot be transferred to our body. It will induce a big problem. Okay, this is told you that this is the extreme case that is dangerous, but actually in the normal status, the blood clotting actually is the leading causes of morbidity and mortality worldwide. So it is characterized by formation of the intravascular obstruction and their mechanical breakage. This mechanical breakage is called embolization. Okay, so the dislodged pieces of clot will be transferred to downstream and form the blockage of the bloodstream. So, and leading to the life-threatening complications. For example, so most of the pulmonary embolus, are arising from the embolization of the deep vein thrombosis, And another disease called ischemic stroke is imminent when the pieces of clot limit or totally cut off the blood flow to brain. Okay, so those are 2 leading deaths. So from these examples, you can see that the mechanical stability of the clot determines effectiveness of the stop bleeding and also decide the outcomes of pathological intravascular blood clot. Okay, so a lot of mathematical models has been proposed or have been provided to give the quantitatively analyze the formation and deformation of the blood clotting. So the key challenge here for mathematical modeling of the blood clotting is the formation and the deformation of the blood clotting is a multiscale and a multi-component problem. So as we said that it first include fiber network, include the platelet, include the red blood cell, and also include some other cells. Okay, like and also the fluid, the blood plasma. Okay, so it's a multi-component interaction. And also it's a multiscale. Why it's multiscale? Because in the small scale, in the nano scale, so there are ligand receptor interaction to form the aggregate, platelet aggregate that you saw from the first video. Okay, this is in the nano scale. And in the cell scale, which is a micrometer scale, or multicellular cell scale, so there are interactions between cell and cell, they are deformed and they are aggregate. So, and also in the large scale, there are interactions between the forming clot and the blood plasma. You can see this is the experimental movie from our collaborator. Okay, so it is a multi-scale, multi-component problem. And also it is a very challenging question coming from the mechanical property. So the forming clot is not a Newtonian fluid. If you learn the physics, you learn that there are fluid that are called a Newtonian fluid or non-Newtonian fluid. So for here, the clot actually, it has both the viscosity property and it also has elasticity property. The elasticity is coming from the fiber network. So in this figure, if you can see my mouse, so the blue part is the network, fiber network, and then the purple is the platelet aggregate. It will form a very strong network and it have the elasticity property. So then it will show that the blood clotting is a viscoelastic material. Okay, so in order to provide a deep understanding about the mechanical stability of the clot, so I will mention the 3 different types of the model from the 3 different scale. Okay, so now the first is on the nano scale. Okay, so in vivo, the blood clotting is characterized by there is agonist called thrombin, so which simultaneously induce the alpha-2 beta-3 binding to fibrinogen. So there is a soluble protein called agonist called thrombin, and then it will convert this thrombin to insoluble material called fiber. Okay, so after a short time, inside the clot, there will be 2 alpha-2b beta-3. There will be 2 alpha-2b beta-3 complex. So one is called alpha-2b beta-3 thrombin complex. So it is connect the 2 platelets, okay, to form the platelet aggregate. There is another alpha-2b beta-3 complex called alpha-2b beta-3 fibrin complex, which is connect the total platelet aggregate and this fiber network. Okay, so in order to understand the mechanical stability of these 2 types of alpha-2b beta-3 complex, we just introduce a dynamics model. It's very simple. It's just a 2 ODE model. Okay, so this was because according to the literature, the biologists think that for this alpha-2b beta-3 complex, they have a 2 binding state. Okay, so one is called the lower binding state. That means what? That means, okay, it's the binding between the platelet or the platelet and the fiber network. They are weak, but they are easy to form. Okay, they call the lower affinity state. And there is another state called a high binding affinity state. That is the binding is strong, but it's not easy to form, or it's hard to form this state. Okay, so during the model, let us assume that P1 and P2 are 2 binding or 2 survival probability of these 2 states. Okay, then I suppose you have learned some ODE, so then we can introduce this basic dynamics model. If we do not learn ODE, we will revisit this model during the mathematical modeling class, okay? But I can give you some explanation here. So here my Q1 is called the forced unbounding rate. That means how fast this bounding is breaking, okay? Of course, this Q1 will depend on the force, how much force is acting on this complex, okay? So then it is, this Q1 will fall in this, it's called Boltzmann distribution. I think you have learned this Boltzmann distribution in the physics. So there is a Q1 0, it means that it's called a force-free unbounding rate. That means if there is no force acting to this system, it still has some probability to break. So this Q1 0 is a force-free unbounding rate. And my F is the rupture force. That means how much force is acting on this complex, okay? Then you can see that, okay, this is my model. And also how R21 and R12 is the interconversion between these two states. That means that my lower affinity can have some probability transfer to a higher affinity, okay? And my higher affinity can transfer to the lower affinity, okay? So there are totally about 8 parameters in the model, okay? So now I said, okay, if I do some model simplification, that's the set. We just assume that the interconversion between these two states are very fast. And we just assume that P is the total survival probability of these two states. Now I do not distinct these two states, just sum them up to be the total survival probability of these two states. Then the previous 2 ODE will be transferred to this 1 ODE. And there will totally 6 parameters in my model, okay? So there is one important parameter introduced here, it's called C0. This is told me that in the initial, the ratio of the lower affinity and the higher affinity, the 0 means in the beginning, before the force is adding to the system, okay? So, okay, I have the model, but I have 6 unknown parameters. How to get these parameters? So in order to get these parameters, I just fit my simulation result, this all your model result, with the experimental result, okay? So I have experiment collaborators, so they did some experiment. So then by fitting their experimental result, the parameter is summarized in this table A, okay? So the experimental rupture force profile interactions of alpha 2b beta 3 polyfiber, monofiber, and the fibrinogen are shown in the circle, blue square, and red triangle, okay? All these are the experimental results. So my simulation results are shown in the line. So it's confirmed that our model, the result is consistent with the experimental data. So that's to confirm this model is useful, okay? Now, let's look at this experimental data and the simulation data, okay? Because they are consistent, now I can explain the model or explain the mechanism behind the experiment by my model. Okay, so the experiment shows that, so you can see that this is the alpha 2b beta 3 fiber or fibrin complex. So this red part is the alpha 2b beta 3 fibrinogen complex. You can see that under the rupture force or under the force from 20 to 100 pK, so the survival of the fibrin complex is much higher, which means the fibrin complex is more stronger or more easy to survive, okay? So this could, how to explain this? So the experiment could not explain, but we could explain through the parameters that is fitted by the model, okay? So it could explain in 2 ways. First, we said that there are 2 bounding states. One is lower, one is higher, okay? So first, you can show that for this parameter, Q10, this is for the lower affinity on the force-free bounding rate. You can see that for this 2 is for alpha 2b beta 3 fibrin, it's much lower than the alpha 2b beta 3 fibrinogen. That means, this means for the fibrin complex, it's hard to break, okay? For the low affinity complex, okay? This is the first reason. The second reason is I think there is a two states. There is another one called a strong affinity, which is strong but hard to form. So the last column told us that for the alpha-2b beta-3 fibrin complex, it has more. This is the ratio. So the one over this one told you how much alpha-2b beta-3 fibrin in the complex. Okay. So this will tell you that there are more strong affinity in the alpha-2b beta-3 fibrin complex. Okay, that means the fibrin complex has a more strong affinity, and for the lower strong, it's also hard to break. Combine these two reasons, we can explain why the alpha-2b beta-3 complex is much stable than alpha-2b fibrin complex. Okay, this is the explanation. So the next step is how to use this model. So what's the kinetic application for this model? So the clinic application for this model is told us that during the clinic, if we targeting the platelet binding to fibrin rather than platelet aggregation, maybe it's a good way to increase the therapeutic indices of antiplatelet agent. So it will tell you which part we should target to resolve the thrombosis. Okay, so this is the first part. So any questions currently? You can always feel free to ask questions. Okay. Now let us move on to the next level, to the cell level. So just I said that inside clot there are plenty of inside clot there are plenty of cells are trapped inside. So especially there are a lot of red blood cells. Okay, so we know that the red blood cell normally is in the biconcave shape. Okay, but you can see this figure. This is also from our collaborator in UPenn Medicine School. So they found that in the clot there are a lot of red blood cell which is compressed and then heavily deformed from the biconcave shape to this polygon shape. Okay, so how to model this? Okay, another important problem is so as the vessel, there are the red blood cells interact with each other and also interact with the vessel wall to form the clot. How to understand the individual cell mechanical property on the stability of the clot? Okay, so we will provide two types of model to understand this. Okay, so neglect all the details here, just to give you a brief introduction here. Okay, so I assume that my membrane, so I think in the biology class, you know that on the cell membrane, actually there are plenty of things like alpha helix and a lot of channels and some lipid bilayer, okay, and a lot of things there. And it's sometimes it's not just smooth, it's rough, right? But for here, just for simplicity of our model, we assume that my cell membrane is homogeneous. Okay, it's just like homogeneous, it's smooth. Then I can use that there is an energy called, you just know the name, it's called Health-Rich energy in the mechanics and in the mathematics, which can mimic or model the bending rigidity of the cell, okay, of the cell membrane. Okay, so another two important property of the cell is, okay, during the deformation, the cell volume does not change and the cell membrane surface area does not change, okay? So they always keep a constant. That's what's because the fluid, like the water or plasma, is called incompressible, inside or outside, okay? And also for the cell membrane, because it's formed by the lipid bilayer, so there is a property called inaccessibility. So it cannot stretch too much between these two layers horizontally. So then it's called local inaccessibility. Okay, so these two properties are modeled by introducing Lagrange multiplier. We have learned this in the multi-variable calculus. Okay, so Then so this is my Lagrangian multiplier, Lagrangian. Okay, then by doing some energy variation, so this is, as I said, Lagrangian will give you a model which will give you the horizontal velocity. This is my horizontal velocity, this is t, and the normal velocity of each point on the membrane. Okay, so this v and t will give you the velocity of each point on the membrane. Then how to evolve the membrane? It's very simple. It's just a particle, right? So it is just equal dx dt is equal my total v. My v has two directions. One is in the normal direction. One is called v multiplied by n, and then one is in the tangential direction. Okay, so it's a very simple ODE. That's the dx dt equal v to evolve the particle. But the difficulty is behind that, how to calculate my v, how to calculate my t. Okay. Now I have the model. Even though a lot of coding behind that, let us just show how to calibrate my model. Okay. So every time when I build the model, I have to compare with experimental data or theoretical data to validate or calibrate my model, so that I can confirm that my model is useful in some sense. Okay, so this model is calibrated by comparing with the experimental data, which show the stretching deformation of the red blood cell. Okay, so the red blood cell surface is represented by the triangle mesh of the surface, and also you can see that there are under the cell membrane, there is called a cytoskeleton. So the cytoskeleton is modeled by a network of interconnected viscoelastic spring. So there are a lot of springs connected with each other to model the viscoelastic property of the cytoskeleton and the spectrum. Okay. So during the experiment, so this is my red blood cell. So they had two optical tethers in the blue color, and then they stretch to the two opposite directions. Okay, so these black symbols are the experimental data to show the diameters along the large axis and along the short axis. If this one is the short axis. Okay, so the red dashed line is my simulation result. So again, it's agreed with each other quite well. Okay. So this is a movie to show the deformation of the red blood cell under the stretching force of 90 picnewton. It's very, very small force. You can see that the red blood cell is stretching in this direction where the force is ended in this direction, and the shrinking in the perpendicular direction. Okay. Now I said that we want to model how the cell inside the clot changing from the biconcave shape to this polygon shape. Okay, so this is a movie to show from the UPenn collaborators. So show the different view of the red blood cell. So it's a change to this polygon shape from the original biconcave shape. Okay. So in order to model this, I introduce this setup. I have one cell sitting inside, and then six cells around it. Okay. Then I let this 6 cell compress the center one. This is just a the simplest case. Okay. Then let us see what happened. Let me see. Okay. Then when the cell compress to the center, you can see that this is the zoom of the center cell. It's changed the biconcave shape to the polygon shape. Okay, so you can see this is a polygon shape, and then so this is our preliminary result. Okay, so for here, I just show the deformation of the membrane. The fluid inside and outside, I mean the cytoplasma and the blood plasma, are not considered. This will introduce a lot of problems. So in order to include the plasma, so I introduced the second type of model, which is called phase field. So maybe you heard in some talks. So the phase field is like you have a label function. Label function is like this, okay? So I introduced a function called phi, which is the label function. So the outside fluid, which is in the blue color or in the cytoplasma, is valued at -1. Okay, it's always equal -1. And the inside the cell is another type of fluid. It's called, the value is always equal 1. Okay, so this is the outside fluid, this is the inside fluid. Okay, fluid 1 or fluid 2. Okay, then there is a sharp transition. Okay, this is the sharp transition. It's mimic the thickness of the cell membrane. Okay, so if you remember the tangent function, so this is the tangent function. Okay, so it changes from -1 to 1 with a very, very sharp transition area. Okay, so my phi or my label function in the phase field method, or sometimes it's called a diffusive interface method. So it's like in this way. You just understand like a label. So my outer fluid is -1, my inside fluid is 1. Just use this one, and then my interface, just the intermediate theory, right? -1, there is always a point because it's continuous function, so it's always pass through 0. So my 0 is the center of the membrane, okay? So this is the calculus 101, right? So then you can learn, okay, so I have a 0, phi equals 0 to represent my interface or my cell membrane. Then I can track my cell deformation by this label function. Okay, this is some basic idea about the phase field method. Okay, this is now a little bit complicated. So this is the model is developed by the variation method, but it's for the PDE. Okay, but just to give you some basic idea. What the first equation means? I said I have a label function, but the fluid, like the cell, will move in the vessel, right? Due to the blood plasma. So then my U is means the velocity. I just use the phi to check how my cell moved. Okay, you just understand that. This is the first equation, is to track my cell motion. Okay, neglect all these details to this one. Okay, so this is this rho partial U partial T. This U is called a very famous equation called the Navier-Stokes equation. Okay, to model the fluid mechanism, changing of the fluid. Okay, so I have the fluid, I have the cell. Okay, so this is the two basic concepts. For the others, it's just to model the local accessibility, the compressibility of the fluid. This is just some details I will neglect here. Okay, this is my model. Again, so there are two challenges. First, this is a very, very complicated system. I cannot write the theoretical solution or analytical solution for this equation. So how to introduce some numerical method to solve this equation. Okay, so this is from my model. I have to solve this model. Okay, but in order to solve this model, I have to make sure that my numerical method is reasonable. So then I just do some calibration. The numerical analysis is called a convergence study. Okay, if I refine my mesh, if I refine the time, I can see the convergence. Let's make sure this is some basic idea about the numerical analysis. Okay, we will neglect this part. Okay, so now we do some simulation. First, this is a red blood cell, which is in the beginning, in the initial, it's banded. Okay, and then I removed all the force. Let the red blood cell bounce it back. So you can see that it's bounced back to its original biconcave shape when with time evolves. Okay, so there is another important thing in the numerical analysis is we do not, because the simulation need to run a long time. So we do not want my simulation, sometimes it's break. So in order to make sure my system can always stable, so we need to check the total energy. So the total energy of the system. So you can see that the total energy of this system, because there is no external force acting on this system. So the energy should always decrease. So this is my numerical simulation to show that. Another thing is, as I said, that the total volume and the total surface area of the red blood cell should be conserved. Okay, so now this is to check my total volume and my total surface area during the deformation of the red blood cell. It's always constant from the numerical part. Okay, so this is the first step, that my numerical, I change my model to the numerical model. Okay, so there is a gap. So this told you my numerical model for the numerical solution for the model is acceptable. Now I need to calibrate my model. I need to calibrate my model is reasonable. Okay, so how to check the model? A little bit, yeah, this one. Okay. I set up, there is a experiment like this, okay? I have two plates, the upper plate and a lower plate. And then there is a cell sitting in the center, okay? Then I move these two plates oppositely. So the upper plate move to the left, and then the lower plate move to the right. Then it will form a shear flow, okay? It will form a shear flow. Then let us see what happened, okay? If my internal fluid and outer fluid has almost the same viscosity, you can see that in the beginning, the cell has a little bit rotation, and then the cell rotation, this long axis angle with the horizontal does not change, but the cell membrane actually still moving, okay? It's just moving by looking at this red circle. It's tracking one fixed point on the membrane. So it's do the rotation on the membrane. So the circle is always keep in this direction, okay? So this is called tactiling motion, okay? Now there is another setup said, okay, how about I increase the cell plasma viscosity? Then you can see the difference, okay? So the cell will keep rotating, okay? So so the red circle is still the fixed point on the cell membrane, okay? So in this case, this is called a tumbling motion of the cell, okay? For this tumbling motion of the cell, there is an analytical solution. For the given long axis of the cell and the short axis of the cell, there is an analytical solution called Jeffrey orbit, okay? So this is the time evolution of the Jeffrey orbit of the angle. I mean the long axis angle between, the angle between the long axis of the cell and the horizontal of the experimental setup. So you can see that my circle, red circle are the simulation result. So you can see the simulation model have a good approximation with the theoretical model, theoretical result. That shows that, okay, this model is acceptable for the theoretical analysis. Okay. Now, because the model, I said I can accept that, now I do some prediction and do some analysis. Okay, the first thing is I said that the cell membrane has some property called inextensibility. So why this is important? That was because, let's move on, move back. You can see that the first cell, if I consider the cell is a local inextensibility, that means that locally the cell could not deform too much or could not be stretched too much. Then the cell will block at this stenosis, or you can see the narrow neck of the vessel. Okay, it will block there because it cannot have heavily deformation. But if I remove this constraint, I allowed the cell can have a large deformation locally. That means my membrane can stretch a little bit much locally. Then what happened? Okay, so in this way, if I allow the heavy deformation locally, the cell can pass through the channel. Okay, but actually this can tell you that if we remove this constraint, the total surface area actually increase when you pass through this channel and then come back after you pass through the channel. Okay, but if you keep the constraint, it's always almost a constant. It have a little bit perturbed because it's a Lagrange multiplier. It's not exactly conserved, but it seems that if I have this Lagrange multiplier, it's preserved pretty well. Okay, so it told you that the inextensibility gives you a very important property for the cell passing through the channels, the narrow channels. Okay, the second one is according to some disease. So you know, for the diabetes or some other disease, so the cell that my red blood cell normally is in the biconcave shape. Okay, so the surface volume ratio is the largest one. Okay, but during some disease, the cell will become much round, much spherical. Okay, it's become rounder and rounder. Okay, in this case, the surface area ratio will become much smaller. Okay, now let us see what happens. Okay, if my cell has a smaller surface area ratio, that means the cell become much spherical, then it will block here. That means it's much easier to form the block or to form the clot at the narrow region of the blood vessel. But if my cell is the normal one, that's in the biconcave shape, it can induce deformation and then pass through this narrow region. Okay. So another important property is about the rigidity of the red blood cell. Okay. So I said that the cell membrane is a rigid body, so it has some elasticity. So if my cell is a very, very strong connected by the spring, or it has a large bending modulus, so it's like a rigid body, okay? So it's passed through have some bounce back here. But if it's very soft, so it can induce a very large, you can see very large deformation and then pass through the channel. For the large channel, now currently my channel is I think it's a 3 micrometer. Okay. However, in the experiment they found that there is a threshold. It's a 2.4 micrometer, so that no matter your cell is how soft, you still could not pass through this narrow region. Okay, now let us see what happened in the experiment, in my simulation. Okay, so now I narrow down my channel a little bit from 3 micrometer to 2.4 micrometer. Okay, so let's first check the rigid one. Of course, the rigid one, it will have some bounce, but it will block, okay? Because it cannot have a large deformation. Of course, we assume that it's a block. But okay, we said, okay, how about the soft one? The soft one, we assume that it can have a large deformation. So let's see what happens, okay? It still shows that the red blood cell under this channel width is also blocked because the local extensibility, because the competition between the force on the cell membrane. Okay, so just to confirm our model simulation result with the experimental result, they are consistent. Okay, so these are two models in the cell scale. Okay, of course, my model actually could be used for the simulation of the multi-cell interaction. Okay, because there are thousands of millions of cells in your blood vessel, right? So here I just simulate two cells passing through the channels. So they interact with each other, and then there are some force to avoid that they overlap each other, to repel themselves when they meet with each other very close. Okay, so this just to show some basic result about the interaction of the cell. Okay, so now let us see. Okay, to the much larger scale in the macro scale. Okay, in the large scale or in the blood vessel scale. Okay, so first let us take a look at this movie. So this is a movie to show the formation and the deformation of laser-induced arterial clot in mouse. So you can see that in the beginning, the heavily active platelet will form a close packed core region. So because the clot is heavily deformed, so they can packed very close to each other. So it's called the core region. And then it will, some less active platelets will form the shell region. It's looped packed. So this, you can see this, this blue part is the shell region, okay? And also during the formation of the clot, due to the interaction between the clot and the blood plasma. So some pieces of the clot are teared off from the clot surface due to the interaction, and then form emboli, and then be transferred to the downstreams. Okay, so in order to mimic the formation of the embolization, which is very important, we give another model. Okay, again, I said that in this case, in this largest scale, there are a lot of components in the model, right? So in the movie, you can see that all these small dots, they are small platelets, okay? And then inside the red part is marked the fiber network, okay? And then also the blood plasma, and also there is a core region and the shell region, okay? So there are different phases. It's called multi-phase flow, okay? In order to model this multi-component interaction, again, I just introduce different labels. Let's use the phase field that I mentioned previously. Previously, I just have two fluid, right? Fluid 1 and fluid 2. Then I just use phi 1 minus 1 is fluid 1 minus 1, sorry, phi equal 1 is another fluid. But here, because I have 3 or 4 components fluid, I have to introduce several labels to distinct this first fluid, the second fluid, and the fluid, and and platelet fiber network, and the core region and the shell region. Okay, so this is just like show the binary tree to label different fluid or different components. Okay, so the model is derived by the method called energetic variational method. If you took my Math 101 class, in the beginning, I told you the story about what I did in the research. So that was this one. It's called energetic variational approach. So because we believe that all the models should be consistent in the original physics law, right? So the constraint behind that is, so there are some energy, and then there are some kinematic assumptions, for example, the conservation of the mass, conservation of the momentum, okay? So the whole concept of the energy variational method is I define my system by the energy, the whole energy in the system, okay? And then I defined how much dissipation or how much energy is lost from the system. It's called dissipation, okay? Then the changing rate of the total dissipation is equal how fast I lose the energy from this system. So this is called energy dissipation law, okay? Now I just need to define my energy in the system. So it has, for the system, what I can imagine is as 3 parts. First, I have the fluid inside. The fluid always has some kinetic energy induced by the velocity, right? So what is the kinetic energy? It's just half of rho u squared, as we learned in the physics, okay? The second one is because I have a different component. So there are some entropy, okay? There are some entropy or the mixing energy between these different components. You learn the physics, it's like C log C. This is what you learned in the physics, okay? And also I said my material is not just elastic, so just a viscous material. It also has elastic property. So elastic will give you another energy, elastic energy. So I have this 3 energy, okay? So this is my energy in the system. And also I have some dissipation in the system. So what is dissipation? That means which induce the energy lost is either transferred to heat or to another form of energy. So for example, the friction, the traditional friction of the fluid, because it changed the energy to heat or the other energy. So it's the trivial dissipation. So this is my first term, the friction dissipation. The second term is because, sorry, the third term is because there are interaction between different components. So there are inconvertible mixing. So that means that there is only one direction mixing. So this is a local energy dissipation due to the interaction between different components. Okay, so then I can build my model. It's very complicated, but again, it's the same file. So the first one is I use the Navier-Stokes equation to mimic the fluid velocity. Then the left is used, this suite is used to track different components, the red blood cell, sorry, the platelet, the fiber network, and the whole clot. And then the last one is a mimic. It's called, if you learn the physics, it's called the gradient deformation tensor. Okay, so to model the elasticity of the clot. Okay, and for the others, this is just to mimic the growth, because during the clot for deformation, it also has some clot platelet can touch the surface of the clot induced by the fluid. I will also consider this in my model. Okay, anyway, so now I began to do some simulation. I have a setup, which is taken from the snapshot of the experimental data. So it has the core region, which is heavily compact. Okay, it's heavily packed. It's hard to deform. Okay, and then loose packed the shell region in this light color, and then it has a long tail due to the interaction. Okay, so this y-axis about 50 micrometer. This long, this x-axis is about 200 micrometer. Okay, so now again, how the model, how to do, to show the people my model is acceptable, it's reasonable, right? I need to do the calibration. So the model is calibrated by computing some protein, because we said that the fluid or some material can always pass through the cloud. Cloud is like a proximity. There are a lot of pores inside the cloud. Okay? So the model is calibrated by computing the protein or some material passing through the cloud, and then compare with experimental data. Okay, so there is an experiment in the literature to show the protein passing through the core region, which is in the solid triangle, and then passing through the shell region, which is shown in the solid circle region. Okay, so the solid symbols are for experimental result. And then my simulation results are shown in the open circle symbols. You can see that they are quite well met with each other. To confirm that the result is, the simulation is, or my model is reasonable, or is calibrated. Okay, but for this calibration, I didn't calibrate the material property of the cloud, especially for the elastic material property. In order to confirm my material or my cloud has elasticity or viscoelasticity property, I check that by do the so-called creep recovery test. Okay, so the setup like this. I have a cloud sit in the bottom, and then from 0 to 1 second, okay, I add a fluid from left to right. The fluid will from left to right. Then it can see that cloud will elongated because the fluid is blow from left to right, okay? Then the deformation of the cloud keep increase, okay? Now, if I stop my fluid after 1 second, okay, then what happened? You can see after 1 second, there is no force. Then due to the elasticity of the material, it will slowly recover back. Okay? So the deformation is recover. So this is a recover phase. But because it's not a full elastic material, there are some viscosity. It will induce some loose energy. So then there will have some permanent deformation like this here. Okay, so this is just to confirm my material or my clot has this viscoelastic property in the model. Okay. Then I do some calibration further on. I will neglect this part. Okay. Now I do further study, also predict the relationship between the clot permeability and the stability of the clot. So because my main focus is how to understand the embolization of the clot. What induced the embolization of the clot? Of course, there are a lot of reasons. But for here, we said there is one important reason is called permeability. So what is permeability? So permeability is a very important feature to describe how easily the fluid can pass through this material. Okay, so the model predicts that the clot with higher permeability are more prone to form the embolization. Okay, so this one you can see the permeability is 2 order higher than this one. Okay, you can see there is a elongated shape and then detached from the cell, or detached from the clot, and then forms embolization. Okay, but for this one, when the clot with a lower permeability, that means the fluid is much harder to pass through the channel. The clot, it's more stable. There is only a little small pieces of clot platelet detached from the clot. There is no large size embolization formed from this lower permeability clot. Okay, so the model is, or my simulation result is semi-quantitatively agreement with experimental data. So especially the deformation of the clot and then the rupture of the clot. Sorry, the embolization, the formation of embolization through the rupture, and then the final stable form of the clot. That means that, and the final, after the interaction between the fluid and the clot, the only part left is the core region. So this is also consistent with my simulation that only the close-packed clot is left. Okay, for almost the shell region, which is formed by loose-packed clot, will be removed or will be teared off and then transferred to the downstreams. But sometimes it's in the small platelet, sometimes it's in the large embolization. So it's like in this large embolization. If it's in the large embolization, it's very dangerous. Okay, so why it's dangerous? Because as we said that it will form like it will be transferred to our brain or to our lung, right? So if, for example, there are a lot of small arterial in our brain. So if my clot or pieces of clot is transferred to our brain, there are a lot of places have a very narrow region. It's called a stenosis. It can be induced by mechanical or some disease. Okay, so if my clot is very soft, what happened? What happened is okay. So when cut through the narrow part, so you can see that the downstream blood flow is limited almost down to 0. But when it passes through this narrow region, it's my blood flow can recover. So okay, it's fine as long as the blockage time is very short. So because finally my blood flow can come back. So there will be enough oxygen or nutrition to support my neuron or glia and other tissues in my brain. So they will not induce too much problem. However, if my clot is large enough or stiff enough, like this simulation, it will induce a big trouble. Okay, so you can see that when it comes here, it's trying its best to pass through this narrow region because the stiffness of the clot, it will stop here and then totally limit or cut off the blood flow. So this one is the blood flow at downstream. That means there is no blood flow as downstream. Then it will induce the stroke. It will make damage to our brain tissues. Okay, and then induce the stroke. Okay, so now I have shown the different scale include a multi-component model to show the mechanical stability on the mechanical property of the ligand receptor, the individual cell, and the whole plate aggregate on the stability of the clot. And three different scale models, but with a different ODE or PDE models. Okay, so the problem is, okay, so what lost in the model? Okay, so here I didn't consider the reaction behind that. So if we recall the first video, you can see that there are a lot of coagulation factors, like coagulation factor 10, and also other coagulation is called the cascade. Okay, so there are a lot of reaction behind to do the formation of the clot. But here, I didn't provide enough information to the clot formation. I only consider, especially for my large scale, I only consider the deformation of the clot for given formed clot. Okay? So currently, I'm working on the mathematical model for the reaction part to model how the platelet is activated and then how by the agonist and then how the platelet aggregate is formed due to the reaction. This is my current and the future work. Okay, so I will stop here by showing my collaborator. So my collaborator from Notre Dame. So Julian, he and Mark Albert, they are my previous postdoc advisor. And then my collaborator from UPenn Medicine School. And then for the competition part is my advisor in the when I was in Canada in the Field Institute, and then two collaborators from University of Dundee. So they are currently working. So the work with individual cell deformation is we work with my Dundee numerical group. Okay, so I think I will stop my talk here. It's almost 1 hour. I will stop my talk here and then take your questions. Any questions? Hello? Can you hear me?
Yes, we can hear you.
Okay, great. Thank you. So any questions or any comments?
This is very sophisticated.
Yeah, the biology is very sophisticated, but the first two model is based on some ODE model. So we will revisit part of them later on in the class. But just to give you some, actually the purpose of this talk is not show this very complicated model, just to show the applications of the mathematical model in the biology. But you also need to have some physics and a solid mathematical fundamental information. You can build model, and then you can tell you have the you can show the power of the mathematics, and then have the collaboration to solve the problem coming from industry, coming from the biology, coming from physics. So this is the purpose of the talk. I said the applied math is very powerful, but you have to learn a lot of stuff, including math, including biology, including the physics. That is also, I think, for the liberal arts, that is the advantage of our the liberal arts training. Okay. Any other comments or questions?
What is the percentage of applied mathematicians in your team working on this project? Like, do you have biologists and physicists working also with you, or it's only applied mathematicians, or it's mixed?
Yeah. So thank you for the question. It's very important for the team building. So for this clotting part, just as I show you, sorry. Okay, so Julian is a mathematician, applied mathematician, and he's working on the model. And Huaxiong is also a mathematician for the modeling with me. So these are two modeling part, collaborator. And and also we said that we have we have 3 members, including me, is for the modeling part. Okay, this is the interface. Okay, now for the biology collaborator, we have this Oleg Kim and John Weisel. Of course, John Weisel, the whole lab in the UK. So they do a lot of experiments to give us the biology input and a lot of data such that we can calibrate our model. This is the biology part. Okay, so, and also because we just as Joyce said, it's complicated model. In order to solve the model, we have to ask help from the numerical part. So the Professor Lin and then Dr. Shen from the University of Dundee, of course, and also Julian, so they also working on the numerical part to solve the complicated model. So then we combine these 3 parts together to build model, sorry, to get the experimental data, to build the model, to solve the model, and then come back to explain the experimental data. This is how to build the model, how to solve the problem.
How do you coordinate the work between those 3 teams? It seems very complicated to me because they deal with different things, and it's very interesting.
Yes. So especially it's a train. I was trained for during my whole I almost trained in the biology and the physics part at the interface about a long time, 7 years. So I should see that in the beginning of this training is very tough. Especially I cannot read the biology word, it's a long word, and I cannot memorize that, I cannot understand that. And then sometimes when I talk with the biology collaborators, I do not know what he or she talk about. But after a long time training, so by reading some material, by evolving, so you can, okay, I'm knowing what's your problem in the biology, and then transfer it to my math problem. So, but of course, it will take some time to do the coordinate between the teams. But you know, the motivation is that sometimes you can use what you learned to solve the real problem. So then you can see, what I learned is very useful. So then I know what I can do and I know what I cannot do. So for what I can do is good. For what I cannot do, I will try to learn if there are any tools from the pure math or from other part could solve. So that will motivate to learn more from both biology and math.
Thank you.
Okay.
I have a question.
Sure.
I don't remember if you said that. What's the clinical benefit for this study?
So the first one. Great. So let me come back here. So I said that in our cloud, so there are a lot of binding or interactions between the different components, right? So especially there are 2 binding. So one is called between platelet platelet. So this is called just like there is a rope to connect to build connection between 2 platelets. It's called alpha 2b beta 3 fibrinogen complex. Okay, this is the one connection to build the aggregate. Okay, so another one is between the whole aggregate and the fiber network. That means a lot of the fiber network will form a net to cover the platelet aggregate and to stabilize. Okay, so this is called fibrinogen, so alpha 2 beta 3 fibrin complex. Okay, so because we want to, in order to cure want to resolve the clot, we want to find a way to remove this connection so that my clot can be resolved, right? So previously, there are a lot of medicines are designed to break this connection. Okay, so but previously, most of, at least I was told that, I'm not fully sure, but at least I was told by our collaborator, it said that, so previously we are more focused on the platelet-platelet interaction, the first one, okay? So now it told you that what our target should more focus on the platelet aggregate and then fiber network. If you break that, then the clot is more easy to be resolved and then to remove the dangerous.
Wait, I am a little confused. Yeah. So so there are two ways to to make connection, and one is between how do you pronounce platelet?
You just said two cells.
Okay. One is cellular, and then is like the clot with all the not cytoskeleton. What's that called? The framework.
Like a lot of net, like a lot of rope to cover the.
Okay, so if a drug is designed to resolve all the ropes, then the clot will be released.
Yes, will be resolved. Yes.
And then, yeah, it will be released from the web, but not resolved because the connection between the cells is not destroyed, right?
So but because just as I said that, so there are two forces. If you remove that strong forces, okay, because like you have two shell, so one is strong shell, okay. If you break the outside the strong shell, then for the inner shell or the weak shell, it could be break by the fluid and the clot interaction. So it will be break other small forces. Okay, so in order to, for example, if you want to break something, the hard part is you want to break the stiff cover, right? The shell. If we break the hard cover, then for the left one it's easy, right? It can be break by another small forces. So this tells you that if you break the hardest one, the strong shell is the connection between the cell aggregate and then the network.
Okay.
Is that clear?
I'm still confused. Can I annotate? Okay. So I want to ask, are we going to break like at the blue interface or just to break the green?
Yeah. We will break this just as you plot there. So we will break all this red part connect with this the green part. That's blue dot.
Oh, the blue dot. Okay. Yeah. So then the clot will get released, and because all the weak forces in between the cells, it can be resolved by forces caused by the fluid. And okay. Yeah, because I was thinking about potential like clotting at other places, maybe at the lung, and that would be very dangerous.
Yeah. Just said sorry, let me start this one.
Okay. Thank you very much.
Pronouns for the COVID-19, so it will form the clot in the alveoli and then stop the blood flow. Will induce a lot of problem, and also for the pulmonary embolus, it's called the shunt. It's called dead space. It will induce a lot of damage to our lung tissue because there is no passing through this area. Then there is no nutrition. Of course, the alveoli will die, right?
Yes. Okay.
Okay. Any other question?
Oh, I have another question.
Okay.
So I don't remember that. Have you mentioned like which size? Oh no, let me rephrase my word. Does the size of the? Can I speak Chinese? Sorry, sorry.
Yes, I can translate.
Oh, thank you very much. 我想问的就是，它不是要凝血吗？它是要堵住一个地方，堵的那个地方的那个大小，就是要被堵的那个破的那个地方大小有被考虑进去
Yes. So Joy asked, did we consider the size of the stenosis of the narrow part, or the size of the clot? Okay. So first, the clot can partially block the vessel. So it also will limit how much flow will transfer to downstream, right? So it will decrease partially, and sometimes it will fully blocked. So especially for the region that is induced by disease, it has some abnormal narrow regions. So for example, in my cell model, I said that the narrow region has a lower bound. It's called, it's about 2.4 micrometer. So normally my red blood cell have a very large deformability. So it can pass through very, very narrow red blood cell, blood vessel. It can induce large deformation that we can pass through. But it seems that there is a narrow, at least for the experiment in the glass, okay, in the glass. So they found that there is in such case, the cell cannot pass through or cannot induce pass through this narrow region by some large deformation. So the clot can be induced by some abnormal narrow region of the blood vessel, and also it can be induced by some inflammations. Okay, so it will grow very, very fast. For example, the coronavirus, so it will grow because of the inflammation. So it will induce very fast at the beginning, and also it's depend on for example, the viscosity of our blood flow. Okay, this also can induce, sometimes it can induce the clot growth very large, so that it can fully block by our blood vessel.
Oh, so yeah, I was thinking, are we talking about one red blood cell here or a clot?
Oh, for here it's red blood cell, but just as I said that the red blood cell is one of the main reason to induce the blockage of the narrow region. So my last experiment is a show for the clot passing through this narrow region, right?
Oh, so okay. The last experiment is so complicated. I couldn't understand. Okay.
Yeah, this is just to show the inside is clot, the small pieces. It can pass through when it's soft. It cannot fully blocked when it's stiff.
Okay.
Yeah.
Okay. I see.
But there are a lot of work. We are also working on how to model the adhesion force between the clot and the blood vessel wall. And how about actually in the real case, my blood vessel wall can shrink and then can bounce it back, right? So how to model the motion of the vessel wall. So this can also be modeled. Okay. No questions? If there are no questions, I think I can stop here. And thank you for everyone's time to listen to this very complicated talk. Thank you for your time.
Thank you for giving us this talk. That was a very nice one.
Okay, so thank you so much, and I wish I can see you soon, either on Zoom or in campus. Wish you all safe anywhere. Okay.
Thanks a lot for your talk. Guys, we'll upload the video on our YouTube channel, so you can always rewatch it if you want to like relook at some parts of it. Also, we'll ask for Professor for the presentation so we can attach it to the YouTube video.
Sure. Okay.
Bye, everyone.
Bye. Bye-bye. Bye-bye.
Bye.